Hello and welcome. In this video, we're going to talk about what a logarithm is. We've defined it a little bit in previous videos, but we're really going to formalize that definition, and we're going to talk about the inverse properties of logarithms and exponential functions. So let's go ahead and jump right in. So as we mentioned before, the simplest way to think about a logarithm is that a logarithm is an exponent. A log is an exponent, and logarithms came to be really to serve the purpose of representing an incredibly large number or representing an incredibly small number in a similar way that you could think about scientific notation. It came about as a more concise way to represent something really large or really small. When we say a log is an exponent, we mean this logarithm, the answer to it is the exponent that makes this statement true. So really we're asking ourselves, b to what exponent gives us n? That's the easiest way to think about it. Because of that, we can sort of create a language going back and forth between logarithmic form and exponential form. Log base b of n is equal to x because b to the power of x is equal to n. Log base 2 of 8 is equal to 3 because 2 to the third power is 3. So when you're looking at this, you're saying, this is the base of my log, just like it's the base of my exponent. That base to what exponent, because a log is an exponent, is 8. So if we let b and y be positive real numbers and b is not equal to 0, the logarithm of y with base b can be denoted log base b of y. And that's how you would say that out loud, log base b of y. And we can see the correlation between the two different forms, the logarithmic form and the exponential form. So we would say b to the power of x is equal to y because what exponent, a log is an exponent, what exponent takes us from b to y? So let's start by really just focusing on translating back and forth between those two forms, and then we'll look at some sample problems. So log base 4 of 16 is equivalent to 4 to the power of x is equal to 16 if we simply switch forms between the two. 3 to the power of 0 is equivalent or equals y could be rewritten using logs. So log base 3. 3 is the base of the exponent, which means it will also be the base of the log. The y is what's on the other side of y is equal to 0. So now that we've done a couple practice problems going back and forth, let's actually just do a few more so we can really get this translation between forms down. All right, so let's start by translating from the log form to the exponential. Just remember, the b that is the base of the log is also the base of your exponent. Your exponent, because a log is an exponent, is going to be what the log statement is equal to. And that will be equal to x. So b to the power of y is equal to x. Similarly, here the base is 6. To what power? Well, the log is the exponent, so the exponent is 2, is equal to 36. Why don't you go ahead and pause the video and rewrite 3 and 4 on your own, and then unpause the video and see how you did. All right, hopefully you have had time to try these on your own. I'm going to go ahead and identify my bases. A log is an exponent, so I'm next going to identify my exponents, and then what they are equivalent to. In this case 1, in this case 16. And the cool thing about this form is for examples 2, 3, and 4, we can actually confirm that these statements are true just based on math that we already know. 6 squared is 36. 4 to the power of 0 is 1. 2 to the power of 4 is 16. So that's converting from the log to the exponential form. If we're working in the opposite direction, we really just start the same way. We're going to say log base, what's the base of this exponent? It's 4, of 64, actually I don't want to do that in red, of 64 is equal to our exponent because a log is an exponent. So whatever your exponent is, so even on number 6, the exponent is 4, a log is an exponent, so I'm going to put 4 on the other side. What's my base? Log base 3, because that's the base of the exponent here, of 81. This is like saying 3 to what power 4 is 81. All right, go ahead and pause the video and rewrite 7 and 8 using logs, and then unpause the video and see how you did. Okay, hopefully you had time to do that. Log base 5, log base 10. I'm going to put my exponent over here, which is 3, and my exponent over here, which is -1. And then 125 and 0.1. So now that we can go back and forth between the two forms, that also means that if we throw a variable in just in one spot, we could evaluate that. So what I mean by that is, what if I asked you for a log base 3 of 9? We could ask ourselves 3 to what power is equal to 9? And that's a question we can answer. 3 to what power is 9? 3 to the second power is 9. So being able to go back and forth between these two different forms is going to allow us to evaluate logs at various values. And before we practice that, let's just identify a couple of special relationships, because for some reason they're a little bit harder to get used to seeing in the log form, and I want to make sure we make those connections. One of the first relationships I want to talk about is what happens if this number is a 1. It actually doesn't matter what the base is. This is asking us, what exponent do I raise the base to get 1? And that's always going to be 0. And we know that to be true because whatever our base is, anything to the power of 0 is 1. So anytime you see a 1 as this sort of non-subscript number with our logarithm, that's going to mean that the exponent that makes that statement true is 0. Something to the power of 0 is going to give us 1. The next relationship to recognize is if you see the same number in both places, what to the power or what exponent takes us from b to b? Well, that's going to be 1. B to the power of 1 is going to give me b. 3 to the power of 3 to what power gives me 3? That's always going to be 1. So let me write that example down. Log base 3 of 3 is going to equal 1 because 3 to the first power is equal to 3. So thinking about it in exponential form is really helpful. The other thing I want you to be prepared to recognize is what happens if the number is getting smaller. So if you look at number 10, we're going from 5 to 1 over 25. So we're starting with something and we're getting to something smaller. If you think about exponents, what makes a number get smaller is going to have a negative exponent or a fractional exponent. So remember that negative exponents reciprocate. That's how it's possible for me to go from 5 to the power of something and then end up with 1 over 25. So if you see a fraction, that may be an indication that you need to use rational exponents or negative exponents. If you see a number getting smaller, again, that might be a reason that you might be thinking fractional or negative exponents. So let's work through these practice problems. I'm going to show you what I want you to be thinking about in steps, but I want you to be clear in how your answer is written. So what we're going to think about on number 9 here is that this is asking me 4 to what power is equal to 64. It's asking me for the exponent because a log is an exponent. Yes, you are going to get tired of hearing me say that, but I hope you don't forget it. So this question is asking us 4 to what power is 64? So 4 times 4 is 16. 16 times 4 is 64. So in this case, the question mark must be 3. The exponent that makes this true must be 3. But how are you going to write your answer? You can't write something equals something else. This question never had an equal sign to begin with. So you're going to rewrite the original statement. Log base 4 of 64 is equal to 3. 3 is the exponent that takes 4 to 64. So similarly with number 10, we're thinking 5 to what power is going to give me 1 over 25. Well, the first thing that I notice is that 1 over 25 could be rewritten as 5 to the negative second power because 25 is 5 squared. How do I make it go to the denominator of the fraction? I make the exponent negative. So that must mean the exponent that makes this statement true is going to be -2. Again, your final answer should be the original statement rewritten. The answer is the exponent. The answer is not question mark equals -2. That's not answering the initial question that was being asked. All right, I'm going to encourage you to pause the video and try numbers 11 and 12. I'm going to give you a hint on number 11 to try and rewrite 0.2 as a fraction instead of as a decimal and see if that helps you out. Okay, hopefully you've had time to pause the video and work through this. What we're thinking on number 11 is 5 to what power is 2 over 10. 0.2 is 2/10. Well, let's go ahead and simplify that. 2 over 10 simplifies to be 1 over 5. What's going to make me reciprocate this? A negative exponent. And since I want to just move the 5 to the denominator, log base 5 of 0.2 is going to be equal to -1, because 5 to the negative first power is going to give me 1/5. 36 to what power is going to give me 6? Well, 6 is the square root of 36, and the square root is the same thing as having an exponent that is 1/2. So log base 36 of 6 is equal to 1/2, because 36 to the power of 1/2, which is the same thing as the square root of 36, is equal to 6. So a log is an exponent. You're answering the question, what exponent gives me this value? What exponent takes me from the base to the next number? So you may have noticed when you were looking at your calculator when we were evaluating exponential growth and decay models that there are buttons for log and buttons for natural log. In fact, we used natural log, or we used second natural log, to find the E button on our calculator. So that is going to lead us to a couple of different types of logs that I want to make sure that we mention. A common log is a log with base 10, and that is written as log log. Sometimes you will see that it actually doesn't have a subscript. So when we first learned about variables, we talked about having 1x, but how most of the time people just write x because the 1 is sort of redundant to write in front. Logarithms do the same thing. Log base 10 is the most common log base. So if there is no number written in the subscript, it means that there is an invisible 10 there. The log button on your calculator is already base 10. If you push that button, it automatically is base 10. So if you're actually trying to evaluate something of a different base, we're going to need to talk about the change of base formula, which we'll talk about in the next video. But log base 10 of a value, that's the button that your calculator is going to give you. Now, if we wanted to have log base E, that actually has its own button. That is natural log. The natural log is the inverse of E. Natural log is something that's used a ton in sciences, and it's used very heavily in calculus, as opposed to the common log, which is used a lot less in calculus and higher levels of math. Both of them are important. You need to know how to work with both of them, and you need to know how to evaluate them in different ways on your calculator. So if you have a scientific calculator, go ahead and grab one or open a tab and pull up a scientific calculator so we can talk about how to evaluate logs on your calculator. All right, so I have grabbed a scientific calculator here. What I want to point out are the buttons that you're going to be using. Both of them are here. So natural log, if you're evaluating log base E, or if you see ln, ln is how we refer to natural log. And then the common log, log. Now notice it doesn't have a subscript here because this is log base 10. So what we're going to be doing on our calculator right now, even though it doesn't say this, is we're going to be evaluating log base 10 of 8. If you go onto your calculator and you press log of 8, and you're going to get a value, 0.903, that is the value of log base 10 of 8. If you wanted to find a different log base, like log base 2 of 7, you're going to have to use something called the change of base, which we're going to talk about in a different section. As of this moment, we're not learning how to do anything unless it is base 10 or it's base E, meaning we're using our natural log button. So this is going to give us 0.903. For natural log, I'm going to go ahead and clear this. I'm going to press natural log of 0.3, which really means e to what power is 0.3, and that's going to give me negative 1.2039, so I'm going to round that to negative 1.204. So go ahead and pause the video and try 15 and 16 on your own, and then unpause the video and see how you did. All right, so hopefully you had time to try that. Log of 21 is going to be equal to 1.322. And natural log, let's clear this, natural log of 0.54 is going to be equal to negative 6.16. Negative 6.1, oops, sorry, negative 0.616. There we go. So it is important that you understand how to use your calculator to evaluate these. It's also important that you understand what exactly you are evaluating, right? This is saying 10 to this exponent gives us 8, which makes sense. This exponent should be less than 1 because I'm making this smaller. E to what power gives us 0.3? Again, that makes sense. E is 2.7. This is getting smaller. It's going to have to be a negative exponent. So now that we've talked a little bit about switching forms between the exponential form and the logarithmic form, and now we know this notation for common log, we're going to do two last things in this video. We're going to talk about some inverse properties, and then after we talk about those inverse properties, we're going to actually talk about finding the inverse of exponential and logarithmic functions, which we touched on just a little bit in the first half of chapter 6. So let's look into that. So we've talked about that the fact that logs and exponential functions are inverses of each other, and we in fact have defined them to be that way. What that means is if we look at the composition of those inverses, as we did in a previous chapter, if we plug one into the other, we should get x out. Whichever way we're plugging, right? The composition of two inverses, if I plug one into the other, should simplify out to be x. So what that means is if I have something like b to the power of log base b of x, that's just going to simplify to be x. If I have something like log base b of b to the x, that's going to simplify to be x because these are inverse functions. Now, it's really easy to say that, but I want to actually help you understand where that comes from, and I'm going to show you one way to evaluate this in this section, and in the next section, I'm going to show you another way that you might like a little bit better. So, inverses undo each other, meaning exponentials and logarithms undo each other. To get rid of a log on each side, I can exponentiate both sides. To get rid of an exponential on both sides, I can take the log of both sides. And we're going to focus on all of those skills in the coming videos as well. So based on this property here, b to the log base b of x is equal to x. Based on this property, this statement is true. 10 to the log base 4, since this is, 10 to the log of 4, meaning log base 10 of 4, because there's no subscript here, is equal to 4. So let's prove this to ourselves. So the very first thing we're going to do is we're going to say, let's actually come way down here so we have more room. Let y equal 10 to the log, I'm going to write a 10 here because we're still getting used to that, base 10 of 4. Now, let's rewrite this. This is currently in exponential form. Let's rewrite it in log form. So a log is an exponent. So we're going to write log base. What's the base here? The base is 10 of y is equal to, the log is equal to the exponent. What is the exponent? It's log base 10 of 4. Now, if these two statements are going to be equivalent, what does y need to equal? Y is going to equal 4 in this case. Now, the original problem didn't have a y, so we can sort of eliminate that and just go with the idea that 10 to the log of 4 is equal to 4. So when we're working through these problems, sometimes it's easier to start with that let statement and to work through that so that we can see how this is going to simplify. Some of you are going to get it more quickly than others. Some of you are going to need to do these steps, but don't worry, I'm also going to show you another way in the next video. But let's do a couple more practice problems like this one. Okay, so number 17 is already in logarithmic form. So we're still going to start by saying, let y equal log base 5 of 25 to the power of x. Now, instead of switching to log form, we're going to switch to exponential form. So what's the base of our log? The base of our log is 5. A log is an exponent, so the exponent is y. And this is going to equal 25 to the power of x. Now, in order for these two things to be equal, we probably need to rewrite 25. And how do we rewrite 25? Well, we know that 25 is 5 squared. So in this case, these exponents are going to be the same. So y is going to equal 2x. What does that mean? That means that log base 5 of 25 to the power of x is equal to 2x. Okay, I'm going to encourage you to pause the video and work through 18 and 19 on your own using the last two examples that I just did with you as a model, and then unpause the video and see how you did. So hopefully you had time to work through these on your own. Step 1, rewrite with a let statement. Let y equal what's already there. Step 2, change form. So number 18 is currently in exponential form, and number 19 is currently in logarithmic form. Go ahead and switch so that they're both in the opposite form. So on 18, the base of the exponent is 10, so log base 10 of y is going to equal the exponent because the log is equal to the exponent. The green part is the exponent. For 19, it's already in logarithmic form, so you're going to switch to exponential form. 4 to what power? Well, the log is equal to the exponent, so 4 to the power of y equals 16 to the power of x. So on number 18, in order for these to be exactly the same, y needs to be equal to 18. So this statement, which I'm going to rewrite here, is going to be the final answer. 18 is what that simplifies to because these are inverses and they're undoing each other. Similarly, I'm going to rewrite as 4 to the power of y is equal to 4 to the 2x, since 16 is 4 squared, which means that y is going to equal 2x, which means, therefore, log base 4 of 16 to the power of x is equal to 2x. So now that we've spent a little bit more time working with these two different forms, let's tie this together with an idea from chapter 5, which was finding the inverse functions. Okay, so some of these steps are going to seem really similar to what we did in chapter 5, but we are tying this into our new type of function, which are logs and exponentials. So we're going to start just as we did on those last couple examples and just as we did in chapter 5 by letting y be f of x. Then we're going to state that we are, in fact, going to find the inverse. And actually, let's go ahead and write this is natural log of x plus 3. We're going to go ahead and find the inverse, which means that we're going to switch x and y. And we're doing this so that the person reading our work can follow our logic. So if we're going to find the inverse, we're going to switch our x and our y value. Now, y is inside this natural log function. In order to get it out, we need to get out of logarithmic form. So the way that we can do that is we can exponentiate both sides, meaning what's the inverse of natural log? It's e. So I'm going to say e to the power of this and e to the power of this. So on the left-hand side, I'm going to have e to the power of x. What we just showed on those last few examples is that if I have e to the power of natural log, what I'm left with is y plus 3 because e and natural log are inverse operations. So now to solve for y, I just need to subtract 3 on both sides. And then as always, we're going to rewrite our final answer using inverse notation. So f inverse of x is going to be e to the power of x minus 3. So if you start with common log or natural log, you're going to have to exponentiate both sides in order to get y disconnected from the logarithm. If you start in an exponential form, at some point you're going to have to take the log in order to get y out of the exponent. So let's look at an example like that. So we're going to start by saying let y equal f of x, which in this case is 6 to the power of x. Then we are going to find the inverse by switching our x and our y. So x is going to equal 6 to the power of y. Now we need to isolate y, but y is in the exponent. The only way to get y out of the exponent is to take the log of both sides. And what base do we want for our log? We want it to be base 6. We want it to be base 6 so that we can have log base 6 of 6 over here. Now, this statement we just showed in those past examples, that's 1, so what's left is our y value. So log base 6 of x is going to be equal to y. And then we're going to rewrite our final answer using function notation. F inverse of x is log base 6 of x. So I'm going to give you 2 last problems that I am going to encourage you to try on your own and then unpause the video and see how you did. All right, go ahead and try out these 2 problems on your own. Hopefully you've had time to do that. So step 1, write your let statements. Be careful, number 20 is using g instead of f, so make sure you're saying let y equal g of x. So step 1, write your let statements. Step 2, state that you're going to find the inverse and switch your x and y. Now on number 20, in order to get y out of the natural log, we need to exponentiate. So we're going to take, and what's the inverse of natural log? The inverse of natural log is e. So we're going to take e to the power of both sides. So e to the power of x is e to the power of natural log of y minus 5. E to the natural log, these are inverses, so what's left is y minus 5. So e to the power of x plus 5 is equal to y. And we're going to rewrite that using inverse notation using g, because this is our g function. G inverse is e to the power of x plus 5. For number 21, we're going to take the log base 11 of both sides. Why 11? Because 11 is the base that we have over here. Then the left-hand side isn't going to simplify at all, but the right-hand side is. 11 to what power is 11? 11 to the first power is 11. So y is already isolated here, so now we just need to rewrite our final answer using inverse notation. F inverse of x is equal to log base 11 of x. So there's a lot of new stuff in this section, and it's a lot to digest. The idea of what a log is, going back and forth between the different forms, figuring out where the buttons are in your calculator, and then using those inverse properties to not only simplify like we did on 18 and 19, but also to find the inverse of an exponential or a logarithmic function. So go ahead and write down any questions you have, go back and re-watch any of these problems, and I look forward to supporting you on this in class. Thanks for listening.